ever pondered over the fundamental principles that shape the theory of computation? Our journey begins with a crucial theorem that stands as a cornerstone in the world of computer science, Kleene's theorem. Named after the American mathematician Stephen Cole Kleene, this theorem is a key result in the realm of formal languages and automata theory. What makes it so special? Well, it establishes an equivalence, a sort of harmony, between three different models of computation. These are regular expressions, finite automata, and regular languages. In essence, it says that these three models are equivalent in their expressive power. This means that any language recognized by one can be recognized by any of the others. Quite a fascinating concept, isn't it? But this is just the tip of the iceberg. So sit tight and fasten your mental seatbelts. Let's dive into the depths of this intriguing theorem and unravel its mysteries. At the heart of Kleene's theorem lies the concept of regular expressions. Regular expressions, often simply called regex, are a powerful tool in the world of computation. They are a concise and flexible means for matching strings of text, such as particular characters, words, or patterns of characters. In the simplest terms, a regular expression is a sequence of characters that forms a search pattern. This search pattern can be used for pattern matching with strings, or to search and replace occurrences within strings. For example, you can use a regular expression to check if a string of text contains the word apple, or to find all instances of A followed by B in a string. But regular expressions aren't just about finding patterns in strings, they're also about defining languages. You see, in the context of formal language theory and Kleene's theorem, a regular expression is a way to describe a set of strings. Let's consider an example. Suppose we have a regular expression that represents the pattern A followed by B or C. This regular expression defines a language that includes strings like ab, ache, and any string that contains A followed by either B or C. Kleene's theorem takes this concept to the next level. It asserts that for any language, there exists a regular expression that generates precisely the strings in that language. In other words, given any set of strings, you can find a regular expression that describes exactly that set and nothing more. This is a powerful statement. It means that regular expressions can be used to define any language that can be recognized by a deterministic or nondeterministic finite automaton. Therefore, regular expressions hold the key to understanding the expressive power of these computational models. So what's the takeaway here? Regular expressions are not just about pattern matching or search and replace tasks. They are a fundamental concept in the study of formal languages and automata. They offer a way to describe sets of strings or languages in a precise and compact way. In essence, regular expressions are the building blocks of the languages we're studying. Now, let's shift gears and explore the world of finite automata. Imagine a labyrinth where you navigate from room to room, following certain rules. This is the essence of finite automata. They are like these mazes, with the rooms being states and the paths between rooms representing transitions. Finite automata come in two flavors, deterministic and non-deterministic. Let's dive into each one. Deterministic finite automata, or DFAs, are like well-behaved mazes. You start at one room, and for each symbol in your input, there's exactly one path leading out. There's no ambiguity. Each symbol in your alphabet guides you to a specific next state. If you reach a state with no path out for a given symbol, you're stuck. The input isn't accepted. Now imagine a maze where a room might have more than one path leading out for the same symbol. This is the realm of non-deterministic finite automata, or NFAs. An NFA can have multiple transitions for the same symbol, or even no transition at all. It's like you're in a magical maze that allows you to be in multiple places at once. If any of these paths leads to an end state, the input is accepted. Though both types of automata seem different, they're just two sides of the same coin. They're both tools for understanding patterns in languages. For every NFA, there is an equivalent DFA and vice versa. This is the beauty of finite automata. They provide different lenses through which to view the same language. Finite automata are the workhorses of many parts in computer science, from compilers and text editors to network protocols and search engines. They help us make sense of the complex patterns in the languages we use to communicate with machines. Though seemingly complex, finite automata are simply state machines that help us understand patterns. So every time you use a computer, remember you're navigating through a maze of finite automata guided by the rules of the language you're using. With regular expressions and finite automata under our belt, it's time to delve into regular languages. Now, what exactly is a regular language? In the simplest terms, a regular language is one that can be recognized or generated by a regular expression, a deterministic finite automaton, or a nondeterministic finite automaton. Each of these models has its own unique way of perceiving and interpreting the language, yet they all arrive at the same conclusion. Fascinating, isn't it? Let's break it down a bit further. Imagine a regular language as a vast ocean of strings, where each string is a unique creature swimming about. Regular expressions, deterministic finite automata, and nondeterministic finite automata are like different types of nets. Each net has its own design, its own way of capturing strings, but ultimately they all have the capacity to capture the creatures of this ocean. Stephen Cole Kleene, the mathematician who we owe this theorem to, established this profound equivalence between these three models of computation. His theorem asserts that these models are equivalent in their expressive power. This means that if a language can be recognized by one model, it can be recognized by all. Put simply, if a net can capture a creature, then all nets can capture it. This is where the beauty of Kleene's theorem truly shines. It gives us the freedom to choose the model that best suits our needs. Whether we're designing a search engine using regular expressions, creating a compiler using deterministic finite automata, or solving complex problems using nondeterministic finite automata, we can rest assured that the languages we're dealing with are regular. So if you ever find yourself in the midst of strings, fret not. Remember, you have three nets at your disposal, each with its own strength, each with its own charm, but all capable of recognizing the creatures of the regular languages. Regular languages, in a nutshell, are the languages that can be recognized by these models of computation. Having explored the components, let's revisit Kleene's theorem as a whole. This theorem, an essential pillar in the world of computation, establishes a profound equivalence between regular expressions, finite automata, and regular languages. Let's recap the key points. For any language, there exists a regular expression that can generate all the strings within that language. This regular expression, a compact notation for patterns in strings, is a core element in pattern searching and data extraction. Next up are deterministic and non-deterministic finite automata. These are models of computation that can transition between states based on input symbols from an alphabet. Kleene's theorem states that for any language, there's a deterministic finite automaton that accepts exactly the strings in that language. Similarly, there's also a non-deterministic finite automaton that recognizes the same language. And finally, we have regular languages. These are languages that can be recognized by regular expressions, deterministic finite automata, or non-deterministic finite automata, a clear testament to the expressive power of these models. Kleene's theorem is more than just a mathematical statement. It's a bridge connecting these fundamental models of computation, asserting their equivalence in expressive power. This theorem is of paramount importance in computer science, underpinning our understanding of regular languages, regular expressions, and finite automata. Practically speaking, it has far-reaching applications. It aids in the design of lexical analyzers in compilers, helps with pattern matching in text processing and data mining, and even plays a role in network routing protocols. The theorem's broad utility makes it a cornerstone in the field of computer science. Remember, every complex concept in computer science, like Kleene's theorem, starts with simple building blocks. It's all about connecting the dots.